Okay. Now, we did say the other day, what was the most important aspect of electricity? The current. What were the two factors that influenced the current? The voltage and the resistance. Right. We've had a look at what? We haven't looked at resistance yet. We've looked at voltage. We've looked at connecting cells in series, parallel, and series, parallel. Right, so we've done that side of it. Now we're going to have a look at resistance, how the resistance affects the current. Okay. I think that's one sheet. Sorry, yes. Right, who else had to show me, who sat here? Back for him. Who else had to show me their notes pasted in? Was Luther the other person? Dylan, weren't you one of them? Are they pasted in? Right, so you've all got page 8 there, is that correct? On top of page 8, you'll see an example that I'd like you to do quickly. It's just a revision example on cells. Okay, if we go through those notes, resistance slows down the current. Okay, so resistance, what did we compare it to in a car? The brakes. All electrical components, even cells, believe it or not, even a battery of cells has got its own resistance. So everything has got resistance in it. Do you think they deliberately put resistance in these things? No. Okay? When people manufacture a battery, they try and keep the resistance of that battery as low as possible, but the electricity's got to flow through the battery. You agree? If you've got a circuit that's got a battery in it and a resistor, does that electricity that's flowing in that circuit, does it have to flow through the battery? Yes, it's got to flow through the copper wire. That adds resistance. Does it have to flow through the resistor? Yes, that's resistance. And I put a big arrow there, so that means big resistance there. So you've got a big resistance there, a smallish resistance in the copper wire. Does it have to flow through the battery? Yes, because it keeps going round. So there's a resistance there as well. So even though you don't want the battery to have a resistance, even though you don't want the copper wire to have a resistance, it automatically does. Everything that electricity's got to flow through offers a resistance. It's like friction. Okay? We try and minimize that resistance, that friction, but it's always going to be there. So all electrical components, even cells, have resistance. Although this is often so low that we simply ignore that resistance. Sometimes we deliberately need to increase the resistance, then we connect in resistors. That's the symbol that I used for a resistor. Okay, why would you want to sometimes slow the current down? It could burn out or not burn out your battery, but use up your battery too quickly. If you don't have a resistor, your battery will go flat very quickly because you've got a high current, fast current flowing, so your battery goes flat very quickly. So yes, that would be a reason to connect the resistor in. Why else? To produce light, okay? If you don't have resistance, you're not going to produce heat, and if you don't have heat, you're not going to get a light bulb glowing. So yes, you'd want resistance there. Where else? Why else would you sometimes want resistance? So if it can only handle 1 amp, and your battery would normally provide 20 amps, You've got to slow that 20 amps down. Otherwise, it's going to blow the components in that circuit. So if you've got earphones, they're not going to need 20 amps of current going to them. Okay? Then your earphones are just going to pop. So you would build a resistor in, so you get a very weak current. That's all you need. Okay? So sometimes you deliberately want to put a resistor in to slow the current down. That's necessary. Let's read on. A resistor can be symbolized as follows. Either, like I've drawn on the board, the old up-down pattern, and you normally write the resistance of it above it. I haven't drawn that omega sign very well. Let's try and get it done a bit better. Okay, it's the Greek letter omega, 10 ohms. Nowadays, that symbol is difficult to do on a computer. You've got to go and manually paste your up and down angled lines. There's no one symbol of that shape on a computer unless you designed it and saved it. So they've now introduced that symbol. In other words, just a rectangular box, and you now write the resistance of that resistor in it. Okay, so you may see resistances shown that way, you may see it shown that way. Both are perfectly acceptable. If you're asked to draw it, both are acceptable. In your matric exam, you'll see it this way. Okay, all matric papers now use that symbol for resistors, no longer that symbol. Right, all happy? Then, there are 3 ways of connecting resistors. And what do you think those 3 ways are? Series, parallel, series, parallel. That's the same as cells. Is that true? Yes. So let's have a look at how we're going to connect cells. Not cells, resistors. Remember, we're dealing with resistance now. It's different to cells. Right, so if we're going to connect resistors in series, let's just remind ourselves, when we connected cells in series, let's say I had 2 volts, 2 volts, 2 volts, 2 volts. What was the total voltage if I had 3 2-volt cells? Was it still 2 volts? Or you saying I must add them, 2 plus 2 plus 2, 6. So if I took cell, 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 is that in series? Each one is 2 volts, 2 volts, 2 volts. What's my total voltage? 2 volts. Are you changing your story now, Jonathan? What have I had written there? It would be 2 plus 2 plus 2 equals 6 volts. So V total, the total voltage would be equal to adding them together. That's what we did when we had cells in series. But if I have resistors in series, let's make it 2 ohms, 2 ohms, 2 ohms. R total equals what? 6, or is it 2? Or is it 1 over 2? Easy. Okay? So when we're connecting things in series, whether it is cells we're connecting in series or whether it is resistors we're connecting in series, we just add them together. And resistors are even easier. Why? How could I make cells more difficult? I could turn 1 or 2 of them around. I could do that, that, and then that. You agree? That becomes a little bit more tricky. Can I just say 2 plus 2 plus 2? No, because how many of them cancel each other out? That one cancels that one, so effectively it's only 2 volts. Okay, I can't do that with resistors. Whether I connect the resistor that way or the other way, it makes no difference. Okay, it still acts as a resistance. So we're all happy with resistors in series. That's simple. That little example there, 100 ohms, 5 ohms, 0,2 ohms, we just add them together, 105,2 ohms. All happy? Just a little note there in a bubble. When in series, simply add together. The more resistors, the greater the resistance. And what will happen to the current? The weaker the current. And what will happen to the light bulb? The dimmer the light bulb. Okay, right. There they go dimmer. So that's why I'm not going to draw circuits now. Okay, let's not have a light bulb. Let's just have a look at the following. So if we had to go through that same little paper experiment that we had the other day, how many cells do you want? 1, 2, 3. Okay, 1 resistor and an ammeter. How many cells? Aren't I changing the cells? No, I'm checking to see the resistance effect. So I only change one thing at a time when I'm doing experiments. How many things have I changed here? I've added an extra resistor. I don't fiddle with the batteries as well. Because if I added an extra resistor and I took a cell out, what effect would that have? Depends. So would you say it was caused because I took a cell out or because I added an extra resistor? But of both, you can't see which is which. This way, any change which happens to the reading on the ammeter can only be due to the fact that I've got another resistor, and you can see what effect the resistors are having. And in my third one, what am I going to do? How many cells? 3 cells still. And what am I going to do? 1, 2, 3 resistors, ammeter. Okay, right. Happy with that? Choose any current. Nice, easy number that we can divide. No, 12. 12 amps. Right, what's my next current going to be? Let's say these resistors are X ohms. X ohms, X ohms. So they're identical. X can be 10, X can be whatever you want it to be. What will this current be? 6. How do you know? Because my resistance has doubled. Okay, so this must therefore half. And now my resistance has tripled, so this must go down to a third, so that will be 4 amps. It's pretty simple. I've used the same battery, so the voltage stays the same, the same, the same. Okay, remember we said we change one thing at a time when you're doing experiments. And that one thing that I changed going from this setup to here was 1 extra resistor. And then I changed one more thing, I put in a third resistor. Okay, right, all happy? So, conclusion, I want you to add another 2 lines underneath that. When in series, you simply add them together. The more resistors, I want you to add after the more resistors in series. We're talking about resistors in series. So add into your notes there, the more resistors in series, in that cloud down at the bottom of that page. The more resistors in series, the greater the resistance and the weaker the current. The lower the resistance and the weaker the current. Yes. Okay. All happy with that? Can I take this off the board? Can I leave that on? Yes. Now we're going to be looking at resistors in parallel. Let's just remind ourselves what we did with cells. if I had one cell, 2 volts, 2 cells of 2 volts each, what was my total voltage in the first case? 2 volts. What was my total voltage here? 2 volts. Okay, those are cells. Now let's have a look at resistors. If I have one resistor, 4 ohms. What's my total resistance? 4 ohms. If I have two resistors of 4 ohms, but they're connected in parallel, what's my total resistance going to be here? So this we said was 4 ohms. Yeah, what is it going to be? 4 ohms. Same as yeah. 2 and 2 still gave me 2. So you're all saying the total resistance there is still 4 ohms. All happy with that? It's wrong. Why? Because it's not. You were taught this last year. Yes, Jock, what were you taught? 1 over R total. Thank you very much. Okay. Now, with cells in series and resistors in series, you treated them the same way. You just added them together, whether it was cells or whether it was resistors. But in parallel, what did you do with your cells? Did you add them? No, you just took one of the branches as your answer. Am I right? With resistors, you can't just take one of the branches as your answer. There's a different way. You would say 1 over the total resistance is equal to 1 over each of the resistances in the branches. You remember that? Who didn't do it? Who doesn't remember a thing? Who was away on holiday? You must have done in grade 9 then. Yes, yes. Okay, so there you are. Now, what is your lowest common denominator here? 4. Okay, 4 goes into 4. Once. 1 times 1 is 1. Plus 4 goes into 4. Once. 1 times 1 is 1. Gives me 2 over 4, which is equal to 1 over 2. Is that my resistance? That is 1 over the total resistance. I haven't asked you to calculate 1 over the total resistance. I said calculate total resistance. So what must you do? You must invert. Therefore, R total is the inversion of that, which is 2 over 1, which is 2 ohms. Okay. Who's confused? No one confused? We'll talk about that in a moment. Okay? Let me give you another example quickly. Let's just do an example which you can do on a blank page in your book. $12 ohms and 6 ohms connected together. Quickly do that one. Let's call that example number 1. I'm going to give you a few examples, okay? Right, who gets an answer of 1/4 ohm? You do? You do? Then you forgot to invert. 4. You did invert. Okay. All right. Let's have a look. You're trying to find the total resistance for these two resistors. They're connected in parallel. You can't just add them together. You do that if they're connected in series. You can't just say take the one branch, because that's what you do when you deal with cells. Yeah, you're dealing with resistors. So you've got to go 1 over R total. We're trying to find the total resistance, remember? But we've got to go around the back door. Is equal to 1 over 12 plus 1 over 6. Common denominator? 12. 12 goes into 12 once. 1 times 1 is 1. Plus 6 goes into 12 twice. 2 times 1 is 2. That gives us 3 over 12. So 1 over R total is 3 over 12. Therefore, R total, I've got to invert it, is 12 over 3, which is, all happy with that? Can I give you another one? Yes.
You gave us cells in parallel, and one back here was
I said to you, when you're dealing with cells, I will always make sure that your branches are the same. Okay, that's one of the requirements for schoolwork. You can't have a 2 volts and a 1 volt. But with resistors, I can. Okay? In fact, with resistors, I can get really nasty. What should we make it? 8 ohms, 4 ohms, 6 ohms, 4 ohms. Right, do that one quickly. You got how many resistors there? 4. How many branches? 3. One of the branches has got 2 in series. You agree? These two up here, the 8 and the 4, they're in series with each other. So what are you going to do with those? Add them together and treat them like one. I did say this afternoon after school, you're all going to be doing a practical. Okay, let's have a look at it. Nikita, what are you going to do? 1 over R total, yeah, is equal to? So you're going to treat these two up here as one resistor of 12 ohms. Good. So you add them together first. Right, what are you going to do now? 1 over 12 plus 106 plus common denominator 12. 12 goes into 12. 1 times 1 is 1 plus 2. Okay, and that's going to give me, so 1 over R total is 6 over 12. Therefore, R total is 12 over 6, which is equal to 2 ohms. Right, we're all happy with that? How do you mean straight to the answer? From where? From there to there. You didn't do this. Did you use your calculator? Okay, that's fine. We'll talk about how you can do it in your calculator in a moment. Right, all happy with that? Now, one thing I want to just quickly pick up on, if we have a look at these two resistors here, which was the smaller of the two resistors? They were the same. So what's my smallest resistance? 4 ohms. Do you agree? My answer came out to be 2 ohms. So when I add two resistors together in, what way are they connected? Parallel. My overall combined resistance is always less than either of my two resistors. Let's have a look at this one. Which were my two resistors? 12 and which was the smaller of the two? 6. When I added them together, my combined resistance was smaller than the smallest of the two branches. Will always be. What's my smallest branch here? 4. My combined resistance smaller than the smallest of my two branches, or 3 branches. If I had a situation like this, just 2 branches, a resistor and another resistor, and this was 0.1 ohms, and this was 1 million ohms, what would my combined resistance be less than? Less than 0.1 ohms, always. Okay, and anyone give me a reason why? Okay, you're actually saying to the electricity, imagine this is the Argus cycle tour, and there's a rockfall on Chapman's Peak, okay? And it's slowing all the cycles down. Everyone's got to go past these rocks and it slows them down, and people see, hold on, the people are not going to finish the race before 5 o'clock, 6 o'clock in the evening. So they open up another route. There's a farmer there who's got a route over his land. Okay. And we let the cyclists go along there. What does that do to the overall rate of slowing down the cyclists? It reduces the resistance, doesn't it? The cyclists can move faster because there are now 2 paths that they can go. Now, both paths are slowing the cyclist down because the one is over through in between the rocks and the other one is on the mountainside. So they both are like resistors. But because they're next to each other and half can go the one and half can go the other, or 2/3 can go the one, 1/3 can go the other, it effectively lowers the resistance. So as soon as you put 2 routes for the electricity to travel, if that wasn't there, all the electricity would have to go through there. You agree? And what would the resistance be? 0.1. Now you bring in another route. And you say, look guys, you can also travel through there if you want to. You agree this, even though it's a high resistance, takes the pressure off that route a little bit. So you're now lowering the pressure. So effectively your overall combined resistance will be lower than your smallest resistance, always. Right, we stop there for today. What time? No, this lesson ends at 5 to 22. 22, time to finish.